there's this mystery about time. What's time? We have now.
And now.
And now.
Yeah.
And what does that mean? Well, according to the laws of nature, the one law that has an arrow of time that tells us that is this second law of thermodynamics. So it's really important because we're going to propose that there's a second arrow of time.
Hey everyone, I sat down with two brilliant minds from the Carnegie Institution for Science, Mike Wong and Bob Hazen. Mike is an astrobiologist and Bob is a mineralogist. They're proposing that we scientists have missed a classical law of nature for centuries, something they call the law of increasing functional information. I know that may sound like a word salad, and we're going to get into it and break it down, but it basically explains how things in the universe, life, minerals, even societies and language, evolve to be more complex over time if they meet a few conditions. Hearing about a new law of nature sounds extraordinary, but not all laws are the same. Some are fundamental and apply just about everywhere, like Newton's laws of motion, and some are more constrained, like the law of refraction. Although I started out skeptical, we dug deep, and I think there's actually something to this. Give it a listen yourself, hear what they have to say, and maybe it will change the way you see things. Now, if you think this podcast is extraordinary, please go ahead and rate us. And you know what? Leave a comment and tell me what you think about their new law of nature. And maybe you have a law of nature of your own. And also, make sure to subscribe so you never miss an episode. Your support means everything and helps us to reach more curious minds just like yours. Now let's get at it. Bob and Mike, welcome to Particles of Thought.
So good to be here.
Hakeem, it's great to see you.
Awesome. First off, man, I've been watching you for years, right? I've watched your videos from back in the day on mineral evolution. I followed in your footsteps and became a Robinson professor at George Mason University. And I taught the course you created, Great Ideas in Science. And what I will say is, number one, you have an amazing name, Hazen. Love that.
You do.
Yeah. And if I owned a dispensary, you're such a thoughtful guy. If my dispensary developed an amazingly thoughtful strain, I would call it Bob Hazen.
Oh, that's it. Hakeem,
What a compliment.
Well, I feel like we got a lot in common, and it's a real bond, and it's great to be here.
Thank you, sir. Thank you. And you, sir.
Yes.
You and I have something in common that my colleagues have called out to me before and, about me before. And I'm going to tell you what that is.
Okay.
It is called swag. But let me tell you what I mean by that. When I say it, I say a scientific wild guess, right? And my colleagues tell me, like, Hakeem, you're not scared to throw out your wild ideas, right? You guys are proposing an actual new classical law of the universe, which takes a lot of courage. And you're young in your career.
That's right.
Where do you get your swag, my friend? Where do you get it?
Oh my goodness. Well, I think I get it by just thinking about our job as scientists. Science runs through, hypothesis generation and then rigorously testing those hypotheses. And a lot of people, when they think about science, they think about people in the laboratory, they think about people at a computer, they think about people at the telescope doing the data gathering and the hypothesis testing. But we also need to generate the hypotheses in the first place. And so science really is about putting forth bold ideas and then going about the hard work of trying to verify that this thing could actually be true about the universe. And so think about what we do as scientists and think about the joy of coming up with new ideas and then going about that process. It fuels me with a lot of passion and also just having great colleagues to do it with.
Yeah.
And just having fun in the lab, in the office is something that I enjoy doing. I love throwing my ideas out there. Some of them could be wrong, and that's totally fine because that's how science progresses too.
It is, but listen, man, as a guy who's been in the trenches, our default setting is on skepticism. And even when you're absolutely right, you present your ideas and your colleagues eviscerate you. And, I hear people in public talking about science, and I feel like, when they say, oh, climate change ain't real, Big Bang isn't real, evolution isn't real, in my mind, I'm thinking that the average person thinks that every 30 years ago, all the scientists get in a room and we decide what's the big lie we're all going to agree on, right? But that's not the case. Even when you're right, they eviscerate you. And yet you have the courage to present. You're putting yourself out there with this new idea. We're going to get to it in a second, but man, I'm impressed that you have that courage. So let's get into it. You are proposing a new law of nature.
We're proposing a law of increasing functional information, which is a law of evolving systems. So basically, it says that in any system that has three main attributes. Number one, that it's made up of many different interacting components. Two, that has mechanisms for generating many different configurations of those components, exploring all the possibility spaces of those combinations of components. And three, experiences selection for function, a metric that we can measure and quantify about a system called functional information will increase over time.
Sounds like speed dating. You bring in a bunch of people.
There you go.
They interact.
Yeah.
You get different configurations. And in the end, babies.
Well, there's usually a selection process that goes on before the babies. But you're right. Ultimately, babies. Okay, so that's the function.
All right, gentlemen, humor me again a little bit. There's some house cleaning of language I need to do, and then we're going to go in deeper. And here's what I mean. You are proposing a new law of nature. Now, one of the things that physicists love to talk with their students about is these words: law, theory, fact. And I often ask my students, rank them from most information to least amount. And they typically rank them fact, law, theory. And I say, no, it's the exact opposite, right? So you chose the word law.
Yeah.
And, there's a ton of laws, and some of them are, not very well known. Like, if you want to calculate magnetic fields, you use this thing called the Biot-Savart law that only physicists know.
Not me, maybe
right?
you.
Yeah, only physicists know, right? And you only do it in classrooms. You don't do that in the real world. But you chose law.
Yeah.
So let's dig into what you mean.
Yeah.
And tell us other laws that are similar so that we have a context in which to place this new law.
Yeah, so first of all, just, a fact is like, I have a balance, I determine the mass of this object. That's a fact. So that's sort of trivial. I mean, a bunch of facts can help you, though, to determine a law, which is a mathematical statement. It basically says, here's an equation that explains how some aspect of nature works. And then a theory is a predictive, larger, overarching structure, like Darwin's theory of evolution by natural selection, which describes, explains, and puts into a larger context a bunch of ideas. And that can incorporate facts and laws and all that sort of thing. Yeah, so we're talking about a law of nature. There's a mathematical description about how one part of nature works. And there may be about 10 or 12 existing laws, macroscopic laws, big word. It just means what we experience. Now, you wake up in the morning, your alarm clock goes off, you have to get yourself out of bed, you're working against gravity, you go to the bathroom, you have hot running water, you make yourself a cup of coffee, which cools. And then all those actions you've just experienced, all those macroscopic laws of nature. Let's talk just real quickly. So, the first one's about 400 years ago. Isaac Newton comes up with the laws of motion. It's 3 statements that just tells you how masses and forces interact. So you can lift up a coffee cup, or you can roll a bowling ball, or you can drive your car or send off a rocket. That's Newton's laws of motion.
Newton also came up with this law of universal gravitation. And this story about, the apple falling from a tree and hitting him on his head was probably apocryphal. But nonetheless, Newton made this very impressive insight that act of the apple falling from the tree was the same process, can be described by the same law of nature as the moon falling around the earth. And so one thing that we look for in natural laws are these equivalencies that bind seemingly disparate phenomena under the same framework. And so that's what makes a law, is that it is a universal statement that can apply to many different situations, many different phenomena at once, and capture them under this umbrella, this very simple, elegant statement. And so that's something that we recognized early on when we were working on this idea that natural laws are built upon these conceptual equivalencies, we call them. This idea that this thing unifies disparate phenomena.
Yeah, a great example of that is the laws of electricity and magnetism. You know, you shuffle your feet across a woolen carpet in the wintertime, you get a shock or you get static electricity. Well, that seems very different from the magnet that sticks to your refrigerator or in a compass needle, but it turns out physicists figured out that these are two aspects of the same force called the electromagnetic force, and that allows us to make electric generators and electric motors, and it even explains a little bit how light works and the way that light travels 186,000 miles per second. All that's tied in this idea of unifying electricity and magnetism as two aspects of a conceptual equivalent idea.
And then there are laws of energy. One of the most important laws of energy is that energy is neither created nor destroyed, but can be transformed between many different kinds of energy. So we've got kinetic energy of things moving, but you also have the potential for that kind of energy when you put a ball like at the top of a hill, and then you can transform that potential energy into kinetic energy by just giving a little flick and then it falls down the hill.
Oh yeah, and then there comes the one that's really important to us, Hakeem, this idea of the second law of thermodynamics. It's a big name. It just means the second law of energy, and it has to do with how energy, and in fact all systems in the universe, change through time. You know, there's this mystery about time. What's time?
Right.
We have now.
And now.
And now.
Yeah.
And you, what does that mean? Well, according to the laws of nature, the one law that has an arrow of time that tells us that is this second law of thermodynamics. So it's really important because we're going to propose that there's a second arrow of time. But let's get to the second law. Isn't that cute, confusing? The second law of thermodynamics is really the first arrow of time. Well, be that as it may, and sorry about that. But if you can think about the universe starting off in a very uniform state, right at the beginning, very uniform. And so it's very ordered. Everything's very consistent. It's just like you think about a giant crystal where every atom is in the exact same position. Well, this is a time when things were really uniform. And then as the universe expands after the Big Bang, you start to see structures. You start to see protons and neutrons, which are those heavy particles that make the nucleus of atoms. Then you start seeing atoms. Then you might see molecules. You see gravity clumping things into stars. You see planets forming. You start seeing structures. Things are getting more and more structured. And all the time it means that you're increasing the disorder of the universe, even as locally you get these very clumpy things.
Yeah.
Let's talk about things increasing and decreasing and why the second law of thermodynamics is different from all of those other laws that we just talked about.
Right.
You know, so take Newton's law of motion, for instance. You know, I'm going to take this beautiful prism thing that I don't even really understand what it is, but I'm going to toss it between my hands. And that's a change through time, but you don't know if I played that tape forwards or backwards. There's really no difference between the two, you know. Take, on the other hand, making an omelet. You know, you've got this egg, you crack it, you put it in the frying pan and you mix it up and scramble it and it fries. If you played that tape backwards, it would look really, really odd. And the same thing goes with the complexification of the universe. A great example of this is the evolution of life on Earth. Life started out as a microscopic common ancestor and then blossomed into all of the macroscopic forms that we appreciate around us today. And if you played that tape backwards as well, it would look very, very odd. And that's an arrow in time.
So it's almost as if you're saying every irreversible process is an arrow of time.
Well, yeah, a lot of irreversible processes can boil down to the second law of thermodynamics, which gives us an increase in entropy over time. So that, you know, making scrambled eggs, right, that can be, you know, described by the second law of thermodynamics. You took this very ordered, nice egg, and then you completely scrambled it and you cooked it, and you're not going to go backwards from that. But we also see increases of patterning, of orderliness, of complexity and functionality through the universe, and that's something that we're trying to add to this pantheon of natural laws that describes that kind of increase through time in the universe.
So you just described a set of natural laws that are fundamental across a lot of what happens, right? You know, Newton's laws of motion, these laws of thermodynamics, they happen everywhere, right? Everywhere. And now you're adding a new law.
We are. We're suggesting that there is a second arrow of time, which is reflected in the fact that we see locally on the surface of Earth, on the surface of other planets, we see an increase in local order and complexity and patterning and the diversity. Minerals, they show an evolving pattern where you start with just a few different kinds of minerals long ago in the history of the universe. Today on Earth, we have more than 6,000 different kinds and they form in all different kinds of environments. We see the same kind of increase in diversity in the formation of atoms. You start in the universe with hydrogen and helium, which are the two simplest atoms, and now we have the whole periodic table of the elements, and you certainly see it in life.
So let's name your new law. Let's state it.
Okay, it's the law of increasing functional information. And I think we should probably begin by describing what functional information is. This is the metric that we're using to describe evolving systems. So it's a metric like mass or charge or energy or entropy. These are things that you can observe in the universe and you can calculate from your observations.
So let me just stop you for a second there. So just like you pointed out that in Newton's gravitational law, it was mass. In your law, the key parameter is functional information.
That's right.
Yeah.
And it increases.
That's right. In any system that satisfies three primary criteria. So first, an evolving system has to be made up of many, many different interacting components. And then there have to be mechanisms for generating numerous configurations of those components, trying out new possibilities. And then finally, those many different possibilities have to be subject to selection for function.
I see. So if we go back to the other law that has to do with evolving systems, which is the second law of thermodynamics, it states that in a closed system, entropy increases, what we typically call disorder, which is a bad definition. What is your this idea of entropy? How does it play into? Are your laws related?
Oh,
the second
man,
law.
Yeah. Well, entropy plays into everything because there's nothing we can do without increasing entropy. We're talking here, where our hearts are beating, we're breathing, our brains are trying to put together sentences that are coherent. And every one of those things causes either electrons to move or chemical bonds to form and break or something else. And every time that happens, anytime you do anything, there is some energy that dissipates out into space and increases entropy. So entropy is always increasing no matter what. So it's the law, okay? It's the second law of thermodynamics. It's the law. We can't, and our ideas are completely and totally consistent with it. What we're saying is that arrow of time, that description of entropy always increasing no matter what we do. Going to sleep, we could be sitting here saying gibberish. We could be speaking in languages that no one understands. Entropy is still increasing. But functional information is different. It only increases if you apply selective pressure. So Am I making sense? Are my sentences? What if I scramble the words and say gobbledygook? It would have no functional information because I'm not communicating. Yeah. But the entropy still is increasing.
Right.
And then I say something coherent. Entropy is still increasing.
Let's draw some boundaries here, because in your new law you have these 3 constraints. In the second law of thermodynamics, there is in a closed system. So when you say that entropy may always increase, some listener may say, oh, what about a refrigerator, right? You're doing work and you're reducing the entropy inside the refrigerator, but on the outside, you're dissipating this energy, right? That hot air that's coming out. Yeah. And so you're increasing entropy in the room, even though you're decreasing it inside the box of the refrigerator. Yeah. So the constraint is really important. So one more time, let's go over your 3 constraints just so that we make it really clear to the listener that you're not saying that in intergalactic space, where there are no large condensations of matter, that this is taking place, right?
No. That's right. And we use the term bounded law to describe exactly what you're talking about, Hakeem, that there are certain constraints that make a law valid for describing that particular phenomenon. Yeah. Okay. And so once again, our constraints, there are 3. First, an evolving system has to be composed of many, many, many different interacting components.
Yeah, okay, they could be protons and neutrons to make atoms. They could be atoms to make minerals. They could be molecules that make cells. They could be cells that make you and me. And it could be a whole bunch of us sitting around together talking about ideas that make a social structure or language. So these are all components.
And the second constraint is that there need to be mechanisms for mixing those components into many different configurations, right? And so this is where I think the second law kind of enters the picture, because a lot of those processes that allow you to sample different regions of configuration space require the dissipation of energy, require the entropy of the universe to go up. And then,
sure, because stars mix up protons and neutrons, and Earth, because of water and rock, it mixes up new combinations of elements. And here we are sitting thinking about ideas and mixing up new combinations of words. You got to have a process where you're trying lots of different things, because if you just sit there and don't do anything new, you're not going to evolve.
Right.
So in a sense, if you were looking at the evolution of complexity on the moon in comparison to the Earth, you would say that the Earth is more evolved.
Yeah, moon is just sort of frozen there, just sort of sits there and does very little. Once in a while an asteroid will hit it, and then you get a little bit of stuff going on. And there may be a little bit of seismic activity, that's, earthquakes and stuff going on. But the moon is largely frozen, but Earth is the most dynamic place you can imagine, with plate tectonics and the mixing of the crust and the mantle and the atmosphere and the oceans and life and all the things we do. It's an astonishing place for trying new combinations.
So let's get to that third constraint of the selection mechanism.
Selection for function, right?
So when minerals form, what's the function?
I love it. You're right, Hakeem, you're just right there. Well, for a mineral, I'm a mineralogist. I collect minerals, I go to museums. So the function of a mineral is not to fall apart. Believe it or not, it's just to persist. So it doesn't evaporate, it doesn't melt, it doesn't transform into something else. It means you can collect it, you can put a specimen on your shelf, or it can make a solid foundation of a continent, so you can build your house on it. I mean, so literally, it's just persistence.
And it's context dependent, right? Because if under different temperatures, under different pressures,
absolutely,
you get different minerals,
correct? You change the conditions, you change which minerals persist.
So here's a question then. So could you compare 2 minerals and say one is more evolved than the other? Just because they are formed under different constraints. Like, what determines the time factor?
What a great question. And it's absolutely true. There are many, the vast majority of combinations of atoms simply don't form crystals. They don't form minerals. They just fall apart, or they evaporate, or they transform into something else. And this tiny, tiny, tiny fraction of all possible atom configurations that actually forms stable minerals some minerals, diamond, is forever.
Right.
What's it for?
Allegedly.
So, yeah, allegedly, I know. Okay, you're right. You can mess up diamonds pretty bad if you want to. But then there are other minerals that form through weathering processes at the Earth's surface, some of the minerals in soils and stuff, that they can be pretty transient. There's some minerals that will very quickly alter in the atmosphere to other minerals, like an iron. Iron is a mineral, but if you put iron outside on a wet, hot day, it'll gradually start to rust and change into a more stable mineral, a rust mineral, which we call hematite. So it's absolutely true. There's kind of a gradation. Some minerals last longer than others. But all minerals that you find in a museum or you can put in a museum drawer represent the tiniest, minuscule fraction of all possible arrangements of atoms, most of which will never form minerals because they're simply not stable.
The simplest thing to recognize is that the fewer configurations that a system can take on and still perform that function, the higher the functional information of that system, right? Okay. So the smaller the fraction of all the possible ways you could arrange, say, the atoms in this coffee cup. I've just spilled coffee, but pretend I didn't.
You rearranged the atoms.
No, I rearranged the atoms, but this coffee cup is meant, if I'm not being too wild with it, to hold coffee. Now, very few of the arrangements of these atoms can actually achieve that function.
Or living systems, right?
Exactly.
If I rearrange your atoms, Thanos style, you're not going to be living anymore, right?
Right?
That's right. That's right.
Yeah. So which has more functional information? A forest or a forest that is on fire?
Oh, that's...
Well, this is where the context dependency comes on. So what is the function that you are trying to quantify the metric functional information? It always has to be relative to a certain function that we're choosing because we're interested in that aspect of the system.
So let me give you an example. And let me give you a simple example.
Wait a minute, hold up. You just went into quantum mechanics territory, right? Because basically you're saying that functional information is observer dependent.
This is the answer to the question, is that function is relative, but not in the Einsteinian sense, just in the sense of everyday experience. So we have this beautiful Nova mug, and it holds liquid. Now imagine these atoms, it's about a mole of something, silicon and oxygen.
It always is, right?
Yeah. So and so you've got trillions and trillions and trillions of different ways of organizing these atoms, and only a tiny, tiny fraction of those organizations holds a liquid, has a nice handle so you don't burn your hand, it doesn't shatter every time you set it down. It's this is really nicely engineered.
And says Nova on
and it says
side.
Nova. That makes it even more special. So the function of this cup is to hold coffee and advertise Nova. That's cool, all right?
Yeah.
Now, if it's a really windy day, we're outside, we're doing this interview, and we've got a sheet of papers here. You say, now it's a paperweight. Okay. So now it functions as a paperweight. I could arrange these atoms in a lot more different ways than this, and probably some that are more efficient as a paperweight. So now the functional information as a paperweight is less than the functional information as a coffee cup. And suddenly, there's a fly, and I want to swat the fly, and so I use this and I smash down it. Well, this makes a lousy fly swatter. So the functional information as a fly swatter is But so it's all context. It's this. The mass is the same. The charge is the same. The magnetic field is the same. I mean, all these other physical variables that we've grown up with and we've learned about, they're constant. They don't change. The function is contextual, though, and the functional information is dependent on what we decide is important. And that's really weird for a scientist.
Does it require a consciousness then? Because quantum mechanical observation, the measurement problem, right, doesn't necessarily require a consciousness.
Not at all. No, because if the function, sure, for us to say that the function of a mineral is to be stable for 1 billion years, then we're deciding, but the mineral that's stable for 1 billion years, whether we look at it or not, has a higher functional information than the mineral that evaporates after 10 seconds. It's just, so the question, Hakeem, the one that really gets at us all the time is, okay, are we imposing on nature something that isn't intrinsic to nature, or in fact, is nature telling us something? Functions really are important. It isn't just the mass. It isn't just the charge, which are fixed, which are independent of the context. maybe context really is important. Maybe in life, the fact that a certain enzyme works and its mutant variety doesn't, maybe that's important.
Clearly it is.
Yeah. So context is important.
So a question for you, does that apply to the entire universe as a whole, or is that, for example, would Earth be one system, Mars be a separate system, the sun be a third system for which this law would hold?
It applies locally to a system where there's a selection. So selection can occur at a star or a planetary scale, but selection can also occur in just one warm little pond, or maybe in a single cup of coffee. So selection can occur at many different scales, but in every case, it follows this law.
So selection, define selection.
Yeah. So we think that there is selection in the universe for a couple of different things. So first is selection for static persistence. This describes an entity's ability to just be exactly as it is without bending to decay and entropy for some time.
Yeah, sounds like a rock, but there are also systems that persist. They're dynamic. You can imagine, for example, a hurricane, where it's very dynamic. It's spinning around. It's constantly sucking in new water, some new atmosphere, energy. So the actual atoms don't persist because they get pushed in and then they get rained out, cycled out. But it's still a very dynamic system that persists for as long as you put energy and mass into the system.
And life is a dynamic system as well, but it's not just selected for its dynamic persistence the way a hurricane is. Life is also subject to this third selection pressure for novelty generation. And why is this? It's because novelty is your ability to experiment with new configurations and discover new functions and ways of being that can further enhance your dynamic persistence. One great example of novelty generation in action is the way that bacteria actually tune their mutation rates such that they mutate faster in more stressful environments, or do horizontal gene transfer, taking different snippets of DNA from the environment more rapidly in hospital settings where there's all these antibiotics trying to kill them. They're trying to experiment with new ways of being to survive and persist dynamically.
But there's also just novelties like creating an eye. So suddenly you can see, and that allows you to do things that sightless organisms can't, or to fly, or to walk, or to swim, or to crawl. All those things are novelties because they open up new configuration space.
This podcast is from the producers of Nova. Nova is supported by Carlisle Companies, a manufacturer of innovative building envelope systems. With buildings responsible for over a third of total energy use, Carlisle's energy-efficient solutions are built to reduce strain on the energy grid. For example, Carlisle's UltraTouch denim insulation, made from sustainable recycled cotton fibers, delivers energy efficiency while being safe to handle and easy to install. Made with 80% recycled denim, UltraTouch diverts nearly 20 million pounds of textile waste from landfills each year. Operating across North America, Carlisle is working towards a more sustainable future. Learn more at carlisle.com. A lot of this sounds like Darwinian evolution. What's the difference between...
In many ways it's like Darwin, because Darwin said three things that are very much like we said. He said, first, many, many more individuals are born than can survive.
Right.
And he said those individuals display different traits. So what are we saying here? There's lots of different configurations, and you generate lots of them. And then there's a selection for those individuals best able to survive and produce offspring. So Darwin's theory of natural selection is a beautiful example of what we're talking about, but it's very specialized.
I think one of the things that we're trying to do with our project is to expand our concept of evolution from that Darwinian paradigm and say that we can see commonalities across all of these disparate systems, one of which is life, but many of which are abiotic systems, things that aren't living.
So we're totally cool with, Darwin's was brilliant, and he came up with this idea long before us, and some people would say, wow, our idea smells a lot like Darwin. It's just, we're saying
more general.
It applies to atoms, it applies to molecules, it applies to minerals and atmospheres and oceans and planets, which are non-living, and the Darwin's specific to living systems.
But what about the universe as a whole? It has many different components. There are, lots of different configurations, and you can say that gravity is a selection mechanism, perhaps.
Yeah, right. And so this gets into the detail of what we mean by functional information versus other kinds of information out there. So just as you have many different forms of energy, potential, kinetic, thermal, radiation, there are different ideas for how to quantify information. One of them is what's called Kolmogorov complexity. It's basically the number of bits you need to describe an object of interest. Right? Now, we think that the Kolmogorov complexity of the universe is static. Just as there's a law of energy that says the total amount of energy in a system should remain constant over time, right? The universe is just made up of many different interacting particles and should take the same amount of Kolmogorov complexity to describe where those things are and what their positions and velocities are at any given time. But just as there's a second law of thermodynamics that talks about this increase in entropy as the total energy of the universe remains constant, we hypothesize that the functional information increases over time as the Kolmogorov information of the universe remains constant.
And that increase can be at a local scale, but also be considered like the whole solar system. I mean, you can imagine different configurations of all of these systems, be it at a atomic scale, an individual mineral crystal grain, or it could be at a planetary scale, or it could be at a larger scale.
Well, entropy is not reversible unless you put in energy or you put in work, and then it increases elsewhere. But in an evolution of a solar system, you start off with like dozens of planetesimals, and then you end up with a few planets, right?
Selection. You're selecting.
But it seems like it became less functional information to me.
Well, it certainly becomes, with greater numbers of planets and fewer planetesimals, but the planets themselves then have a combinatorial richness that's not present in the individual planetesimals, these tiny spheres. So a sphere that's 10 or 20 or 100 miles across just can't do the same things that planet Earth can do. We have plate tectonics. We have oceans and atmospheres. We have life.
Right.
And that's only possible when you evolve to these other states.
All right. You gave a good example in the green room that, the skeptic, which every scientist is, and probably half our viewers, are going to still think that it sounds like you're describing your functional information arrow of time is similar to entropy's arrow of time, but you gave an example of a hole in a cup.
Yeah, this is something just in our conversations just came to mind. Now imagine the function of this cup in its very specific arrangement of atoms is to hold the liquid, a hot liquid. You have a handle, you don't burn your hand. Now imagine if this was very thin or there's a little hole in it. So it's almost the perfect mug, except it's got that hole so it leaks. So its function is not very good. And you say, I'm going to fix this. I'm going to use a little bit of epoxy. I'm going to plug that hole, right? And so you put that epoxy, but you put it in slightly the wrong place. Now, you're going to increase entropy because as that epoxy sets, it's going to cool, it's going to break bonds and form bonds. It's going to do all those things. Every one of those little actions, energy is radiated out into space. But you haven't fixed the mug. It's still got zero functional information because it leaks.
Yeah.
Now, say I do it a little better job and I actually plug the hole with that same piece of epoxy. Same increase in entropy because the epoxy has to set, bonds are forming. You're basically radiating heat out into the universe. But now the cup has functional information at the same time. So functional information always involves an increase in entropy. Always. You can't get away from the second law of thermodynamics.
So let me replace this. Let me summarize. So the second law of thermodynamics always happens. Whether you put the epoxy on the hole where it actually plugs it and it fulfills its function, or if you put it somewhere else on the cup and it does not fill its function, this exact same thing happens with the second law of thermodynamics, but the exact same thing does not happen in the increase of functional information. So they're separate.
They're separate.
And that's why we say that our law of increasing functional information must be consistent with the second law of thermodynamics, but does not follow inevitably from it.
And that's why it's not just a corollary or a lemma of the second law of thermodynamics. It's something new. And the thing that's amazing, Hakeem, the thing that's amazing to us is once you start realizing how this law works, and as these three absolutely critical boundary conditions, it has to be made of a lot of particles like atoms or molecules or cells or people or whatever. So that it has to, and there has to be a mechanism to generate lots of different possibilities, because if it just sits there, you're not going to evolve if you just sit there.
Yeah.
And then there has to be a selection pressure, a selection mechanism. You have to say, I'm going to buy this cup because it works. I'm not going to buy that cup because it has a hole in it and someone didn't repair it very well. So there's a selection mechanism, and universe does this selecting in many, many cases for us. So we see it in atoms, we see it in molecules, we see it in minerals, we see it in atmospheres, we see it in oceans.
Let's talk about minerals, right? So you brought up the fact that, the processes of forming planets increases the number of minerals, right, that exist. And then when life comes around and life adds a lot of, carbon moving around, oxygen moving around, you get a whole lot of other minerals.
Huge. Yeah.
But in the example of plugging the hole, having a consciousness increases a efficiency. So the question I have is, are we just talking about functional information? Are we talking about functional information density? And where does efficiency play into this?
So where we think about that, and this is why this particular proposal for a law, it describes, it explains, but it also quantifies. So you have to say, what are you quantifying? And maybe even predicts. And so where were we going with this?
For example, an arrowhead, a stone arrowhead has more functional information than the rock that it was formed from. But the fact that it's a consciousness doing it, right, that's different from a stone falling down a cliff and changing its shape because it has no function when it gets to the bottom, right? So it seems to me that there are different ideas here that are beyond just functional information. There's functional information density, then there's an efficiency at functional information creation.
So Hakeem, you're really hitting on a critical point here. It's partly how rapidly can you generate new configurations and how rapidly can you select amongst those configurations? The thing that's so amazing about the conscious brain is that rather than having to go to a workbench or a furnace or a potter and say, let's try a million different designs and see which one works, you can imagine them. That's why consciousness is so amazing in the evolutionary, because for the first time in the cosmos, rather than having to actually make the mineral, having to make the atom, having to make the cell configuration, we can imagine them and we can apply the selection process. And now computers can imagine configurations. These are called genetic algorithms.
Yeah.
And they can design configurations of an airplane's wing or a ship's hull or an electric circuit millions of times a second and select. So that's why computers and AI can do this so much faster than even we can. So it has the rate of new configurations and the rate of selection.
So there are those three criteria for an evolving system. And just to recap again, many different configurations, a way of generating, many different components that can go into making your evolving system, many different, there are mechanisms for creating many different configurations of those components, and then selection pressures that pick and choose amongst those. And so what Bob is saying is that in computer algorithms these days, you can very rapidly increase the combinatorial exploration. That's criteria number 2, as well as applying the selection pressure. That's number 3. You can also think of places in the universe or times in the universe where you have some of those criterion absent. So like right at the beginning of the Big Bang, right at the first, the dawn of the universe, you don't have a lot of different components. You also don't have very many mechanisms for operating on selection.
Right.
And so during that first phase of the universe's history, there wasn't a lot of evolution happening until you had stars, which are great mixing bowls of protons and neutrons to create and fashion the elements of our periodic table.
Right.
Cosmologically speaking, going very, very far into the distant future, where the universe is near what we call heat death, you lack criterion number 2, the ability to generate new configurations and experiment, because you no longer have the free energy to do so. The second law of thermodynamics is not really on your side at that point.
Right.
You can think about this in a very much more local scale. Think about Earth. If we have a period of an ice age when the whole surface of Earth freezes over, well, you're shutting down all of those water and rock interactions that creates new environments for minerals. So you're not going to make a lot of new minerals. On the moon today, moon's essentially shut down. There's no dynamic surface. You're not generating new configurations of atoms and molecules, so you don't make new minerals. So our law, it's a bounded law. It only works when you have lots of components that are interacting.
Yeah.
You're generating lots of configurations. Now remember, that can either be physically, mixing up atoms and earth, or mixing up new ingredients when you're trying to bake an apple pie or something like that and testing them, where you have to actually physically make the thing. And now we have our ability, our minds can imagine configurations and select, and computers can generate millions of configurations every second.
We've put our minds and our computers to this problem of stars evolving, and we understand that the sun may fully engulf the earth.
Yes.
And all of your minerals in your brains
Gone.
So what happens to your arrow of time, right? So in the universe, the entropy of so you can apply the second law of thermodynamics to the universe as a whole, right? And some people want to apply some elements of quantum mechanics to the universe as a whole. But your law seems like it is not a universe as a whole type of law. It is under those constraints that you applied. It's in a particular system.
It's a law of evolving systems
in a local environment.
Yes, exactly.
Okay.
Right. But at once we were talking about the constraints upon this law. It is also a very expansive law in that it broadens our minds about what kinds of systems are evolving systems. Classically, we think of evolution as being limited to the biological realm, how life evolves. Darwin taught us the principles of biological evolution. But through the law of increasing functional information, and noting that those 3 requirements, many components, ways of generating configurations from those components, and selection for function, apply not just to biological evolution, but to the evolution of abiotic systems, minerals, atoms, isotopes. That expands our minds.
Is there a way to use this observationally to distinguish organic living systems, even if the life is no longer present, from systems that have not had life?
In fact, this is one of the predictions that our law has made. We predicted that the molecules that life uses, these things like that make your cells membranes, the outside, your
lipids.
skin, lipids, there's the name, and that the different kinds of molecules that are involved in metabolism and so forth, that these molecules are selected for their functions. And so life puts a lot of energy into this manufacturing of lots of copies. For example, the sugar glucose. When you look at a tree, 50% of that tree is this common sugar molecule, glucose. So you're making a lot of glucose and you're not making other things. But in deep space, where there's a lot of carbon and there are reactions that make these carbon-based molecules. In fact, they form a class of meteorites that are sort of black, and you can extract this gunky black stuff from it. Turns out they're all organic molecules, and some of them are the exact same molecules you find in life. Things like amino acids and molecules called bases and sugars, things like that. But they're not alive, and you make this mass of different kinds of molecules.
So is that a yes or no?
So you can actually tell them apart, because you're in one case you're selecting for functions, so you make lots of a few things, as opposed to a little bit of a whole bunch of different things. And even if you take those molecules and you bury them in rocks and you bake them for billions of years, and all you've got is little fragments left and fragments of fragments. The distribution of those fragments from life is completely different than the distribution of fragments that you might find in a meteorite that falls to Earth that has a lot of carbon in it. And we've used this now. We made the prediction and have discovered really a new way of life detection based on those fragments. Is it a meteorite-like distribution of fragments? Not alive. If it's a life-like distribution, it's very different.
Try to put it another way is that I like to think of life as a process, right? And so you can detect the process that life occurred through many different ways that it imprints itself on the environment. One of those, as we've been discussing, is the ratios of these different carbon isotopes. Life's processes tend to prefer one over the other. Another major process of life is evolution. There's an evolutionary story that biases the distributions of all different kinds of organic compounds in a living system away from what geology or a meteorite would create on its own. So the difference between the contents of something that fell from space and something that's been evolving on Earth for billions of years is an evolutionary story.
Right.
And that's at the heart of our missing law.
Yeah.
So let's talk examples. How can this play out or be tested?
Well, one of the ways we've tested it, and this has been published now, and people kind of say, oh, that's pretty interesting, is what's the increase in functional information of Earth's minerals? Okay, so think about Earth's minerals. We know evolve. They go through stages. You start with just those very, very first minerals that were formed around stars, about 25 of them. And then you go and you have the earliest nebular minerals. That's when planets are beginning to form, about 100 minerals. And then when planetesimals come together, you get about 300 minerals. Early Earth forms 1,000. When plate tectonics get going, about 3,000 minerals. When life comes along, 6,000 minerals. It sounds like you're increasing the number of minerals. So functional information. So functional information should go down, right? Because as you get more solutions, it sounds like, well, that's a smaller and it's a larger and larger fraction, not a smaller fraction. But what happens is that in the earliest stages, you're only dealing with about a dozen different chemical elements. And then when you go into nebulas, you're dealing with about 20 chemical elements. And when you go to the earliest planetesimals, 30 elements. When you get plate tectonics, maybe 50 or 60 elements. And so the combinatorial richness of the system, the possible different ways you can arrange atoms, goes up astronomically, even as the number of different minerals only doubles or triples. And so functional information, that fraction goes smaller and smaller and smaller and smaller in functional information. And we've shown that in all of what we call 10 stages of mineral evolution on Earth, we see an increase, an increase, an increase, an increase at every stage. So we looked at the different stages of mineral evolution, and we saw that stage by stage, the functional information increases. But it increases in a really interesting way. Rather than just going, up, it sort of starts leveling off, and you reach a limit. So it looks like mineral evolution is limited to about
functional information.
About 150 bits, it turns out, for Earth.
Got it.
Now, one of the intriguing things is it looks like life may not be limited. It may be what's called open-ended. And that's remarkable. Maybe this is even a definition of life. Life is an evolving system that achieves open-endedness.
So how do you quantify the functional information in living systems?
You had to ask that question, didn't you? Come on, Hakeem.
You led me there.
Yeah, I know. So this is first of all, what's the function?
Yeah.
And that's tricky because if you ask it at the level of
dynamic
a molecule,
persistence.
but if you ask it at the level of a molecule, like a lipid making the cell membrane or an enzyme doing a specific function, that's one answer. If you ask at the level of a cell, that's another. If you have a multicellular organism or a community cells, it's a different thing. If you talk about ecosystems, it's yet a different thing. And so we acknowledge that function occurs at many different levels and they're all interreacted. And so the coevolution is going to be mathematically much more complicated than our initial simple idea of functional information.
Yeah.
We think functional information still applies because there are lots of interacting components. They can adopt many different configurations, and you sample different configurations, and then you have selection pressure. But at what level are you selecting? And that's something that evolutionary biologists themselves don't really understand.
So your conclusion about minerals being bounded seems to be an empirical result. You didn't anticipate it.
No.
But now you're anticipating that life will be unbounded.
Yeah.
It's based on what?
Whoa!
It just feels right.
No, it's just a fun idea. It's a hypothesis. And scientists, we're allowed to make hypotheses.
That's how it works.
And
all right, I want in on this paper where we prove that life is unbounded.
Yeah,
that would be.
Yeah. Well, it may be the case that life isn't truly unbounded, but only exhibits an unbounded characteristic up until this point in the universe, and probably for quite a deal longer, because the possibility space of organic chemistry is so enormous that life simply hasn't had time to experiment with all those possibilities and subject them to selection. It could be the case that in an infinite universe that can experiment with all those possibilities, life would eventually find, it's the wall that it hits up against.
Right.
But so far in our universe, that doesn't seem to be the case.
We're just at the beginning. We're at the beginning of the curve.
Yeah.
We're still on the steep rise.
Too many things to explore, even in a universe of our size, in billions of years.
And I think that's just beautiful.
It is, isn't it?
Yeah.
It means.
But you're biased. Your life.
Yeah.
Think like, one of these celestial beings in comic books, right? Where you're not a living entity. Well, never mind, because they're most interested in living entities anyway, right? So you're right. It is beautiful.
Yeah.
It is. Yeah. A boundless universe, and we're part of it.
We are it.
We are it. And we're generating novelty all the time. This conversation between the three of us has never occurred in the history of the universe. And we're a part of introducing that new information to the cosmos. And I think that is also really profound.
Yeah. And maybe some people who are listening today will select it. And maybe not.
I feel like we experience this law of increasing functional information in our daily lives.
The reason this is so familiar to people is not because they're studying minerals. They're cooking apple pies in the kitchen. They're trying new soup recipes.
Yes.
They're mixing ingredients in new ways, and clever chefs do this, and they can imagine, but they have to try them out. And then people taste them. They say, this tastes horrible. Once in a while, well, that's pretty good. And then you get a really great apple pie, and you say, now let's put a piece of cheese on it, or maybe put a little bit of ice cream, and it tastes even better. So you can't put the cheese on the apple pie until you have apple pie, right?
Right.
And so you keep having to, you start with the apple.
Yeah.
Well, you start with the universe, right?
First you have a big bang. In order to make an apple pie, first you need a big bang.
Let's say you start with the apple, and then you have to cut it, and then you try different spices, and you try different crusts, and some of them work, and most of them don't, and you select, and then once you have a certain thing, then you can do more with it.
Right.
You can make it a la mode.
Another thing, when I worked in Silicon Valley, statistical design of experiments, where you examine all of this configuration space, but you do it in an efficient way. Right? So that you don't have to do every experiment and test every possible configuration, right?
Right.
But every one of us does this. When you're driving your car, when you're crossing the street, when you're calling to order a pizza, you're always thinking about possibilities. Should I do this? Should I do that? And you think through configuration.
Wait a minute,
and
Boomer.
You select.
You don't call to order your pizza.
I don't?
No, you go on your app.
What's that?
What's an
app? Explain. That sounds like a stage of evolution that I haven't gotten there.
All right. Well, let's bring you into the future, my friend. Let's bring you into the future, because there is something that's hot, and it involves a lot of different configurations.
Okay, so we've gotten here. Now what's next?
AI.
Okay,
artificial intelligence.
If you can figure out what's next, if you can predict the next thing that's going to increase functional information, you can make a lot of money. See, this is why our law not only just describes describes and explains things, but it also quantifies and potentially predicts. So you can say, what's the next big thing? And how do I seize on it? How do I decide new configurations that might take us? What's my selection? How can we change selection? Advertising is just a way of changing people's selection criteria. So we see this in our lives. I mean, this is pervasive. It's everywhere. It's not just rocks and minerals and atoms and cells. It's language, it's music.
It sounds like
it's Broadway shows.
An application for someone like McKinsey and Company to use to make corporations perform better.
Oh, absolutely. I think so.
Yeah. Well, Hakeem, you wanted to talk about AI, right?
That's right.
And this future. So we've been trying to tie our law of increasing functional information and the idea of function and selection back to persistence, right? So the reason why certain apple pie recipes persist through time is because they perform the function of being tasty. The reason why certain minerals, we can still pick them up and find them in the natural environment today is because they persist statically. But we also think, in addition to our ideas of selection for static persistence and the selection for dynamic persistence, is a third selection, pressure for novelty generation. And I think this is where AI comes in, because AI can vastly speed up combinatorial exploration and then also selection that helps us leap into new possibilities, to discover new things, to generate novelty at an unprecedented rate. And the reason why, with the invention of these AI algorithms, they've stuck around so long and continue to grow into our daily lives and be things and tools that we use and are embedded in the way that our society functions, is because they help us discover those novel configurations very rapidly.
Very rapidly, exactly.
Yeah.
So how do you know if you're right? How do you test to determine if you're on to something?
Yeah. Well, one of the things is just looking to see if there are any evolving systems. And our definition of that simply means it's a system that over time becomes more patterned, more complex, more diverse, more interesting. But it doesn't involve lots of components interacting. It doesn't involve generating new configurations. It somehow does something completely different.
And what about the opposite, like erosion?
Well, of course, and this is something we've thought a lot about. Once in a while, you'll see systems that simply become less complex. Now, and a good example, imagine Earth, 5 billion years from now, when the sun goes into a red giant state and maybe Earth is engulfed. If not, it's going to be blasted and baked. And we go from 6,000 minerals on the surface, maybe down back to 300 minerals on the surface.
Or death.
Exactly. But in those cases, it's because you're not generating new configurations anymore, and the selection has changed. If the selection pressure changes, if you're no longer selecting for things at 60 or 70
well,
degrees
you certainly
Fahrenheit.
change the context.
Yeah, you change the environment. If the environment
yeah.
changes, so once the environment changes, it's a new system. And you have to say, okay, this is different.
I don't want to wait 5 billion years to test this
No,
theory.
no,
So
that's too long.
one thing that I like to think about as a planetary scientist is testing this theory on Saturn's moon Titan. So in the original paper where we introduced this idea to the world, we had a final section about testing this theory through investigating the complex organic chemistry of Titan's near-surface environment, where you've got all of these organic molecules being manufactured in the atmosphere, interacting with the surface, and potentially being sustained in a dynamically persistent system. This is something that we can potentially test with NASA's Dragonfly mission that is due to launch in a few years and reach Titan in the 2030s.
Nice.
There are other people who are testing it for us, because once the paper came out, we've seen scores of papers by groups that we don't know at all, and they're in fields that we don't know at all. There's a group of cancer specialists who are now using this law to model cancer evolution, going from stage 1 to stage 2 to stage 3 to stage 4 cancers. It turns out it does not follow a Darwinian kind of evolution. It follows our law, and they're using this to model cancer and actually propose new therapies. There are other people who are looking at language evolution and the way the use of words evolves.
Right.
And again, it's not Darwinian, but
Yeah.
it appears to follow this idea of increasing
Interesting.
function.
Interesting.
And there are other examples as well. So these are other people who are testing the ideas by applying them to their own specialties.
I think this is a great example of how what we're proposing has enormous ramifications because we're trying to say that evolution, the process of evolution, is not something that is confined just to Darwinian evolution, to the biological world, but we're trying to be more expansive about it.
Right.
And we're also saying that there is an arrow in time that is driven by selection for function, which can apply to everything from the elements of the periodic table to technological civilizations. And then finally, we're saying that that information is a fundamental parameter in the cosmos, the way that mass or charge or energy is.
Wow, I'm excited.
right,
This
right.
is great.
Well, look,
Wish I had thought of it.
in show off. In the world of physics, we have things that I brought up earlier, like the principle of least action, where if I throw a ball from myself to you, it takes the path that minimizes this quantity known as the action. And, the obvious question is, how does it know, right? So your system also seems to evolve to fulfill a purpose. So how does it know? Are you saying that does this imply that there's a God?
So Hakeem, first of all, let's talk about this word purpose, because that's really a loaded word in science, as you know. So let's not talk about our law. Let's talk about Newton's law of gravity. Now, without gravity, we wouldn't have stars.
Right.
Without gravity, we wouldn't have planets. Without planets, we wouldn't have life. So is the purpose of gravity to form stars? Is the purpose of gravity to form planets?
Gravity is not phrased as a law of purpose.
But it's phrased as a law of how
Force.
the universe works.
It is, but a law of purpose says that it does this to fulfill this purpose.
But we don't say that. We don't say that at all.
You
we
don't?
just said this is how the
The
universe works.
purpose is
it's a
to
mechanism.
increase functional information.
No. That's what we observe. Functional information increases.
It's a consequence.
It's a consequence. It's just an absolute consequence of you have lots of components. They're mixed up in different ways. You're sampling those different ways through selection. And those three criteria, which are just neutral criteria, happen, it's inevitable.
So it's almost like entropy, but you're replacing most probable to most functional.
Yes.
With most functional.
And function requires information, whereas probable requires the probabilistic aspect of entropy. So and it doesn't violate any of the other laws. It basically describes and explains. It doesn't say anything about purpose. Nothing about purpose.
You know what? I had a purpose when I sat down with you two, and that was to understand what the hell you're talking about, my friend, because I was skeptical when we sat down here, right? And now that I understand the boundaries and constraints and the actual word and letter of what you're saying, I'm a lot closer to being convinced.
Ooh.
High five.
Oh, man.
Yeah. Still skeptical, but I'm also skeptical of Newton, and I'm skeptical of Galileo, and I'm skeptical of Einstein.
As you should be.
Hakeem, I got to say something about God, though, because this is because, if you're a believer, if you believe in a creator, then we would argue that you better understand the natural laws, the laws of nature, because that's how God did it.
It's
basically.
a reflection of a creator.
So if
the creation reflects the creator.
So you need to be a scientist if you believe in God. If you don't believe in God, then the laws of nature are all you got. So you better be a scientist.
Well, we're born scientists anyway.
We all
born
curiosity
scientists.
and it's the greatest living you can make.
Yeah, I mean, these brains that we are imbued with as the primates that we are really borderline miraculous, right? What you brought up, that ability to imagine, to simulate, and to imagine that which has never existed. And, I just think of Galileo when he imagined an experiment that you could never do, remove all friction. And he came upon this deep insight, that overturned the great Aristotle and his Aristotelian physics. That is miraculous. And it is an increase of functional information.
Yeah.
Right.
And science is the greatest example because it ratchets up. You have to get to a level of understanding of this before you can understand the next thing. Just like mathematics, you have to develop the simple math before you get the more complex. You see it everywhere. Once you see this, once you see the way evolution works at every scale and every domain, you can't unsee it.
Yeah.
It's just there.
It's there. Yeah. Once you see entropy, you see it. Once you see functional information, you see it.
2 arrows of time.
2 arrows of time. Gentlemen, thank you so much. This has been such a rich and dynamic conversation. I really, really, really enjoyed it. Thank you. I am curious. I love to learn. I love being the guy who knows the least in the room. And you guys have turned my brain in new directions to explore. Now, I want to know more. And I'm guessing that our listeners and watchers also want to learn more. I know you have a book coming out, so please tell us the title of your book, where it can be obtained, and where we can learn more about the two of you.
Hakeem, thanks so much. It's been such a pleasure. Yeah, our new book is called Time's Second Arrow.
Evolution, Order, and a New Law of Nature. It comes out February 10th, 2026.
Love it. Love it. Do you have socials or other places that you can be found?
Well, these days I'm on Blue Sky. My handle is Miquai, M-I-Q-U-A-I. You can follow me there.
Go on YouTube and type in my name, Robert Hazen, and you'll find more than you're ever going to want to watch.
All right. I already did that, and I already watched a lot. Thank you, gentlemen. This has been wonderful.
Thanks,
Thanks, Hakeem.